Hello everyone and welcome back to the good stuff we have been doing. So today in this video we are required to compute this beautiful integral, says the integral from negative infinity up to positive infinity of x sine of x divided by 1 plus x to the fourth dx. So let's get right onto it. How do we evaluate this? Well, to begin with, we'll need to notice that the rational term here is x divided by 1 plus x to the fourth, and it is possible to simplify this 1 plus x to the fourth, point being that 1 plus x to the fourth is equal to 1 plus 2x squared plus x to the fourth minus 2x squared, and this is same thing as 1 plus x to the second power all squared minus square root 2, then you have an x all to the second power, so this will be 1 minus square root of 2x plus x. Okay, no, let's see that I will just write x squared minus square root of 2x plus 1 multiplied by x squared plus square root of 2x plus 1. So this is the way to factor this 1 plus x to the fourth. So now that we can factor the denominator, we will attempt to put this in partial fraction in the form of an x squared minus square root of 2x plus 1, and then you have an x squared plus square root of 2x plus 1. And now without trying to suffer too much, we notice that, let's say we consider the difference 1 over x squared minus square root of 2 minus square root of 2x plus 1 minus 1 over x squared plus square root of 2x plus 1. If we try to take this difference, you end up with something like this. So you have an x squared here plus square root of 2x plus 1 minus x squared plus square root of 2x minus 1, all divided by, if you multiply, then you get a 1 plus x to the fourth power, of course. So this takes out, this is out, so you have a 2 square root of 2x all divided by 1 plus x to the fourth. So basically this x divided by 1 plus x to the fourth that is part of our integral is 1 over 2 square root of 2 times everything. So it will multiply. Let me see. Yeah, so it will multiply 1 divided by x squared minus square root of 2x plus 1 minus 1 over x squared plus square root of 2x plus 1. So now that it is possible to put the rational terms here in partial fractions, so we will attempt to, at least we'll have two integrals, and we'll just pray that good things happen from here. So to begin with, let's bring our expression down below. So the original integral is the integral from 0 to infinity of the terms that do appear here are the x divided by 1 plus x to the fourth power. There's a reason I'm putting the terms in different colors. So you would have all divided by sine of x dx. So this right here would equal to 1 over, let me put the partial fractions term in red. So you have 1 over 2 square root of 2 times the integral from 0 to infinity of what? So you have sine of x all divided by what? X squared minus square root of 2x plus 1 minus the, negative infinity rather, negative infinity. So negative infinity. So minus the integral from negative infinity to positive infinity of what? Sine of x, you divide by x squared plus square root of 2x plus 1, all dx, then dx. So you can see that this terms x over 1 plus x to the fourth was able to allow us to put it in partial fractions. If you don't do this, another way to want to try to solve this integral probably would be like, you're going to maybe, okay, we're going to discuss other possible solutions at the end of this video, but for now let's try to see if we can find a solution. So let's see, now for this, now we need to like We recall that there is a way to handle integral so that the integral from 0 to infinity of, let's say, sine of ax divided by x squared plus b squared dx, and also the integral from 0 to infinity of cosine of ax all divided by x squared plus b squared dx. And we know this is pi e to the negative ab divided by 2b. So now we have a quadratic term, and even if we have a negative infinity, it doesn't matter. This is basically just going to be I think this 2 is going to go out. Yeah, this 2 is going to go out. Yes, this 2 is going to go out. So even if we have if we have a trigonometric term in the numerator and you have a quadratic term, it is possible for us to relate it to this particular integral. And this integral, we have solved it in this channel showing 3 different methods. So that means we are in good shape. So we have 1/2 times square root of 2. For this part here, you have the integral from negative infinity to positive infinity of sine of x divided by, now for the bottom part here, you have an x minus, we could write this as 1/square root of 2, I believe so, because if it's squared, you have an x squared minus 2 square root of 2x, which is something as square root of 2x. And if you take the square now, you have a 1/2, so we have to add a 1/2 here, minus the integral from negative infinity to positive infinity of what? Still sine of x, but then now you would have x plus 1/square root of 2 all squared plus half. So again dx and your dx here. So we're making some progress here, I believe so. Let's zoom out a bit so we can have enough space to write. So making some progress. All we need to do now is to try to see if we can at least make some substitutions, because if we recall, we already said that if we are able to reduce this integral to something like negative infinity to positive infinity of even sine of ax divided by x squared plus b squared dx, or say negative infinity to positive infinity of cosine of ax divided by x squared plus b squared dx, we say that if we're able to reduce it to any of these integrals, then we are done. So we need to badly make substitutions. So on the first one, we would take u to equal x minus 1/square root of 2, and basically the u will be dx. Though if x is negative infinity, u will be negative infinity, and if x is plus infinity, u will be plus infinity. So you would obtain 1/2 square root of 2. On one part, you have negative infinity to positive infinity of sine of x will be u plus sine of u plus 1/square root of 2, all divided by u squared plus 1/2, and which is good because at least something good is going to happen from here. Then you have the u. Then, but on the other hand here, from negative infinity to positive infinity, you have if you have x equals to if you have u to be x plus 1/square root of 2, the x would be, so you have a sine of u minus 1/square root of 2 here, all divided by u squared plus 1/2, and then you have the u. Now I'm using the same u, but it doesn't matter. You could have used v or t, it doesn't matter. Now if we proceed from here, let's zoom out a bit. If we continue in this fashion, this would equal to 1/2 square root of 2, and then you would have, for this part here, you have the integral from negative infinity to plus infinity. So here you have sine of u, then you have cosine of 1/square root 2, and then you have plus cosine of u times the sine of what? 1/square root of 2, and you dividing by what? You are dividing by u squared plus, let's say, 1/square root of 2 all squared. And the same thing happens here, negative infinity to plus infinity of what? So you have sine of u cosine of 1/square root of 2. So you have minus cosine u times sine of 1/square root of 2. all divided by u squared plus 1 over square root of 2 all squared du. Of course, then you are not forgetting your du, I hope so. Now, good things are happening, because from here now, we would notice that we can do some cancellation. Notice that this is sine of u cosine of 1 over square root of 2. Cancel out this sine of u cosine of 1 over square root of 2. And this one, the plus and plus, gives you 2. So we obtain, this is 1 over square root of 2 times the integral from negative infinity to plus infinity of what? So you have a cosine of u sine of 1 over square root of 2 all divided by u squared plus 1 over square root of 2 all squared du. Now notice something, that this is a constant, so this is a sine of 1 over square root of 2 divided by square root of 2 times the integral from negative infinity to plus infinity of cosine of u divided by u squared plus 1 over square root of 2 squared du. Now we are done, except that we can write this as, since it's an even function, we can write this as 2 sine of 1 over square root of 2 divided by square root of 2 times the integral from 0 to infinity of cosine of u divided by u squared plus 1 over square root of 2 squared du. And if you recall, I think for the last couple of days we have been focused and serious on this integral, this classic integral from 0 to infinity of cosine of ax all divided by x squared plus b squared. We say this is equals to pi e to the negative ab divided by 2b, and in this our case here, b is 1 over square root of 2, a practically is 1, and then what again? I think that should be that. So you can see that in this case, this our integral over here would then be equal to 2 times the sine. Let me use a different color here. So let's see, let's use red. So you have twice the sine of 1 divided by square root of 2 all divided by square root of 2. So on this part here, you would have pi e to the negative 1 times 1 divided by square root of 2 all divided by twice times 1 divided by square root of 2. So the 2's cancel out, even the square root of 2 and this square root of 2 cancel out. So you have a pi e to the negative 1 over square root of 2 times the sine of 1 over square root of 2, and that is that. So we are done with the problem. Yes, so that is the official answer. So thank you again. I did mention that I was going to offer what other way can we solve this integral, where you can maybe start with something like, say, f of t to be equals to the integral from negative infinity to plus infinity of x sine of tx all divided by what? 1 plus x to the fourth dx. So in this case, you have f prime of t. F prime of t will produce, say, negative infinity to plus infinity of I think x squared cosine of tx all divided by 1 plus x to the fourth dx, and then f prime prime of t would produce negative infinity to plus infinity of x cubed cosine of tx all divided by 1 plus x to the fourth dt dx. And if we continue further, let's not be lazy, let's stretch our hands a bit. If we continue further, you have f prime 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 of t should be negative infinity to plus infinity of x to the fourth. What am I doing? This is what am I doing? Wait, this one is cosine. So this one should be negative sine. And this one now should be negative cosine of tx all divided by 1 plus x to the 4 dx. So if you take, fourth derivative, if you take fourth derivative, you produce the sine but then you have an x to the fifth there, so you could write it as x times x to the fourth. Yeah, I think if you take the fourth derivative here, respect to t, you will have the integral from negative infinity to plus infinity of x to the fifth power cosine of tx. No, this will be sine of tx, all divided by 1 plus x to the fourth dx. So now we can probably take out an x and write the x to the fourth as 1 plus x to the fourth. So you can write this as negative infinity to plus infinity of x. So you have a 1 plus x to the fourth times sine of tx, all divided by 1 plus so minus 1, of course, minus 1 here, minus 1 plus 1, all divided by 1 plus x to the fourth dx. So if you do simplification, you will have a negative infinity to plus infinity of x. You have an x times sine of tx, then you have a minus, the integral from negative infinity to plus infinity of x sine of tx, all divided by 1 plus x to the fourth. So this is basically our f of this is basically our initial f of t. So you have a differential equation that the fourth derivative with respect to t is equals to some constant k minus the first f of t, and this k can actually be found from the Merlin transform of sine. It is easily found in terms of exponentials, and in that case you now have to solve a differential equation. So this is for people who are obsessed with differential equation to try out. Another way you can solve this problem would be, let's think. Okay, you can use residue theorem, of course. I will explore other solutions in the future, and when I do, of course, I'm going to share with you. So, but for today, thank you very much for watching the video, and please subscribe to the channel. Bye, and do have a nice day.